Hi, this is Miss Park. I'm going to take you into Jamboard, and we're going to use the concept of rectangle again to do some interesting things. So I'm going to create a new Jamboard. Here we are. I'm going to call this one Area Models. Okay, and that's a little bit of a clue of what this is going to be about. So I'm going to use my pen, and I'm going to draw a rectangle. Okay, and basically here's your rectangle, and here we have a width, and then we have a length, and the area of the rectangle is length times width. Okay, we know this. So back in elementary school, when they first taught you how to multiply, they would say to you, so if you have, if you have three things here, and you have two rows of these three things, you can group them. So there's two rows of three things, and I will have three across here, and then there's the two rows. So they'll depict it something like this. I'm not really sure exactly how they would show it, but maybe with objects, buttons, or counters or something. And then you would count them and see, oh, that's six. And as you get through the years, you start to be able to get the concept of multiplication, which is really just that if you have two groups of three or three groups of two, that's going to be six objects. Okay, so that's multiplication. Now we can, as you went a little bit higher in the years, you don't need to be counting things anymore. You just kind of know if that's a 3 and that's a 2, then the number of items in here is 3 times 2. Or in other words, if I broke this up into smaller areas, 3 1x1 squares here and 3 1x1 squares would make 6 1x1 squares. So that would be like 6 square units. 6 square units. Okay, so 3 units by 2 units is 6 square units. 6 squares. Now we can extend this concept. So let's say, so we know that 2 times 3 is 6 and give you an area of 6. So let me go a little bit harder. So suppose it was 2 by 13, right? How would you do this? So one way you could do it is you could take your 13 and split it up into, say, friendlier numbers. So remember back in the day when multiplication was kind of new for you. So suppose I take my 13 and I split it into 10 and 3. Okay, and I'll just split it like that, 10 and 3. So the area of this rectangle over here is 2 times 10, which is 20. And the area of this rectangle here, well, that's a 3 and this is a 2, so that's a 6. So my total area is 26. It's 20 plus 6, which is 26, and that's how I can do that. And so that's helpful because without a calculator, if I had sort of more complicated numbers like 9 times 37, then I could break up the 37 into 30 and 7. This multiplication would be easy to do, 270. This multiplication, this area would be easy to do, that's 63. And now without a calculator, it's not too difficult to add up 27 plus 63. And I'll get 3, and I'll get 3, and I'll carry the 1, 333, and that's not too bad to do without a calculator. Okay, so let me go to, let's write in blue what this was. So now this is multiplication. Okay, so I'm going to go to the next frame, and I'm going to make my numbers a little bit harder. So let's say I have 37 by 29. So that's not so easy to do without a calculator. But what I can do is take this 37 and actually divide it into two parts, 30 and 7. And I can do the same thing with the 29, 20 and 9. Now these smaller areas are not so hard to calculate because they're sort of friendly numbers. So let's go 20 times 30. So the 2 times 3 is 6, times another 10, times another 10. Okay, the 7 times 20 is 140. The 9 times 30, right? We're doing areas here. So the 9 times 30 is 270. And finally, this last rectangle is 7 by 9. And so the total area, I would add them up. And now it looks like a lot of numbers, it looks like a lot to add up, but really so many of them are zeros that it's not too bad. So all of these will add up to a 3. 4 plus 7 is 11, and 6 is 17. Carry the 1. 6, 7, 8, and 2 is 10. Okay, and so that wasn't bad without a calculator. And of course I could get really big. I could go 127 by 68. That's hard to do, but I can split up the 127 into 100, 20, and 7. The 68 is 60 and 8, and do the same thing on the insides, and it's really not bad to add them up together, okay? I think I'm missing a 0. Okay, and so on, and you can add them all up together. So that's the concept of multiplication, is that the area of the entire rectangle is equal to the sum of the areas of the smaller rectangles, and we can have as many as we want. Okay, so that's your multiplication. I'm going to go to the next frame, and I'm going to switch it up a little bit and throw in some algebra. So suppose I have a rectangle. Okay, and the dimensions of the rectangle are 2 and x. We don't know what x is. Okay, x is something. So really what I have here is a multiplication of 2 by x. So how do we break down this multiplication? Well, the 2 is nothing but 1 and 1. 1 and 1. And 1x, so x multiplied by 1, anything multiplied by 1 is just itself. So x multiplied by 1 has to be x. And so this area of this rectangle is also x multiplied by 1, which is just x. So when I add them all up, I'm going to get x plus x, which is 2x. So the area of this is 2x. That's how I know that 2 times x is actually 2x. All right? And that seems simple, but it's actually really not. It's the sum of 1 times x and 1 times x. All right? Let's do another one. What if I had x times x? So let's go like this. So how much is x times x? Well, we don't know what x is. We don't know the quantity that x is, but we know that any number times itself can be written as that number squared. So 5 times 5 is 5 squared. 10 times 10 is 10 squared. So we'll just call it x squared. Okay, so we can do these things. So now, what if I gave you a rectangle that was 3 times x plus 7? All right, so how would we figure out how much is 3 times x plus 7? Really, this is what I'm giving you. So using the rectangle, all we have to do is break up this x plus 7 into an x and a 7. All right, so that whole length is x plus 7. And let's calculate the areas of the individuals. So this is a 3 times x, so that's 3x. And this one here is a 3 times 7, so it's 21. When you add it all up, you get 3x plus 21, okay, which is why, so this is actually the same as this, right? Now, probably the way you learned it is you learned something called the distributive property or distribution. And with distribution, algebraically what it is we learned that when you multiply 3 times x plus 7, the 3 is times everything in this bracket. So it's 3 times the x. It's also 3 times the 7. So all I'm doing is I'm showing the exact same thing, but I'm showing it with the rectangles because that is a visual representation. So we understand exactly what the parts are that are being added together. Now here's the fun part. Actually, you know what? I'm going to throw one more in. I'll throw one more in before I get to my favorite. So what if you had 3x times x plus 7? Okay, then what happens? Well, the x plus 7 is going to be split into x and 7. 3x and x, well, the x times x, we said is x squared. And now it's 3 of those. So that's 3x squared. And 3x times 7 is 21x. So then so 3x times x plus 7 is equal to 3x squared plus 21x. Okay. Okay, let me go to the next frame. So we've done the distributive property. Now suppose I gave you x plus 6 times x plus 4. Okay, now how would we do this? Well, we've seen that we can split up the x plus 6 into x and 6, and the x plus 4 could be x and 4, right? Now let's find the areas of the individual, of the smaller rectangles. So x by x rectangle will have area x squared. This one is a 6 by an x, so that's 6x. This one is x times 4, or 4 times x, which is 4x. This one is 4 by 6, which is 24. And if I add up the areas, what I end up having is x plus 4 times x plus 6 is actually, let's add them all up. It's x squared plus 6x plus 4x plus 24. Okay, and now I can collect the like terms and go, well, that's x squared. 6x and 4x is 10x plus 24. All right, what concept was this? So there's several names for this. So this is actually also distribution, because what I'm doing is I'm multiplying this first item by everything in the other bracket. Okay, so I am distributing. I'm multiplying the x times x plus 6. I'm also multiplying the 4 by x plus 6. Okay, so that is distribution. It's also called multiplying binomials. So a binomial is an algebraic expression that has two terms. Okay, so it's multiplying binomials. Now, it's also called expanding. So let me just go, hold on. I'm going to call it expand and simplify, because here is the part where I expand, and then collecting the like terms is the part where I simplify. Okay, now you may have also learned a little acronym for this last year, which went something like this. It's the x times the x, it's x times the 6, the 4 times the x, and the 4 times the 6. And that acronym is FOIL, which stands for the first term times the first term, the outside term times the outside term, the two inside terms, and then the two last terms. So first, outside, inside, last. I will probably not be calling it FOIL. I like to call it multiplying binomials or expand and simplify. And the reason I'm going to do that is because sometimes we're not going to have a binomial times a binomial. We might have something like this. A binomial times a trinomial, in which case FOIL is not going to work. But if you think about the rectangle, if I can split up these parts, x squared and the 4x and the 1 and the x and the 3. Sorry that it's kind of slanted. I'm not really sure why it came out slanted. But anyway, then I can do this multiplications, and I can see that there are going to be 6 parts that I have to add up for my answer, not 4 parts like here. So by using the rectangle, I know I'm not going to be skipping any terms when I do the multiplication. Okay? Now, not saying you always have to use the rectangle, but I'm showing you why the expansion creates all these terms. Okay? So let's keep going. So now that we've done expand and simplify, that's all forms of multiplication, I'm going to take you backwards. So I'm going to give you a rectangle where we know the area, but I'm going to ask you what's the length and what's the width. So the area is given, and I'm asking you what are the dimensions. Okay, so that's kind of going backwards. So you could say to me, well, that's easy. The dimensions are 3 by 8. But somebody else might say, well, no, the dimensions are 2 by 12 or 4 by 6 or 1 by 24, right? Lots of different answers. So writing a number as something times something is the opposite of doing the multiplication and getting the answer. So it's writing the number as something times something. So I can write 24 as lots of different things, right? I could do this, I could do this, right? And so writing a number as something times something, so I'm going to write that over here. Something times something has a name that you learned last year. And the name is factoring. Okay, so these something times something they're factored. This is factoring the number 24. Now, because there's lots of ways to factor it, it tells us that these methods of factoring it can be factored further. So if I have a 4 and a 6, I can see that I can actually go further and factor those numbers as well. So the 4 can be written as a 2 times a 2, and the 6 can be written as 2 times 3, and none of these numbers can be factored further. So the 24 being written as this 2 times 2 times 2 times 3 also has a name, and that name is fully factored. So an expression is fully factored if it can't be factored anymore. Okay, so here you have your factoring. Let me go to the next page and I'll give you factoring now with algebra. So factoring with algebra, let me give you the rectangle. So remember, when it comes to factoring, we're going to give you the inside. We're going to give you the area as given. And we're going to ask you what goes here. Okay, and now leave it to you to decide what could be length or width. So let's start with width. What could be the width? Could I have, to get my 2x plus 10, could I put a 3 here? So 3 is a problem because 3, like I can't find a whole number that's going to multiply by 3 to give me a 2 or a 2x or multiply by 3 to give me a 10. So it's not going to be 3. Could it be a 5? Well, same problem. 5 times something would give me 10, but it can't give me a 2. So what could it be? So a 2. A 2 would work. A 2 times something could give me 2x, and also a 2 times something could give me a 10. So let me split this up again like I did before. What would have to go up here? So 2, this length is 2, and this one would have to be something so that the product is 2x. So that's got to be an x. Okay, and this 2 times what gives me a 10? Well, 5. So that means that I can write the expression 2x by 10 factored. Remember, factored means something times something. So I can write it as 2, this dimension, times x plus 5. And now this is factored. Okay, so remember, factored means it's written as a product. It's something times something. Okay, and what I just did, writing this as 2 times x plus 5 is called common factoring. The 2 is a common factor of 2x and 10. It means the 2 divides into 2x without a remainder, and the 2 divides into 10 without a remainder. So that means the 2 is a common factor. So I'm going to write that here, that the 2 is a common factor. So what we've done is we've taken the concept of multiplication and gone further and gone backwards. Actually, at this point, I'm going to go back. For this one over here, if you knew, so we want the product to be 24. If you said, okay, I'm going to make the width a 3, how would you get an 8? How do you get the second number? Well, you get the second number by going 24, which is the product, divided by 3. That gives you the second number, or the length, right? So what I really should have written here is that this is also division. Okay, so multiplication goes with expand and simplify. Okay, this is multiplication, and division goes with factoring. Okay, so that's your common factoring. Let's go again, another frame. So now let's have some fun, right? Remember how we said, I'll just do a quick multiplication. So x plus 5, should we take a negative? Let's go negative. Let's do that. Okay, now you're going to have to be okay with a side length of a rectangle being a negative number. Obviously, it's not a real rectangle. We're not measuring it and getting negative, but conceptually, you're going to have to be okay with side lengths being negative because that's what we're going to multiply by to get an area. So area of this rectangle is x squared. Area of this rectangle is 5 times x, so 5x. Area of this rectangle is negative 2 times x. And area of this rectangle is negative 2 times 10. Sorry, negative 2 times 5, which is negative 10. So your total area is x squared plus 5x minus 2x minus 10, which is x squared plus 3x minus 10. Okay, right? So that was the review of multiplying. But now, factoring means I'm going to give you the area. So let me think of a different one. Think of a different one, okay? I'm going to give you the area, and I'm asking you what is the length and width, right? So how do we do it? Well, we look at the pattern that we noticed whenever we multiplied a binomial by a binomial. We noticed that the x times the x will always give us an x squared term, okay? And we noticed that these two terms here will have x's in them because one of the dimensions of those rectangles is x, and that this one here will not have any x's in them. This will just be a number because it's a number times a number. So I'm going to start to fill in the parts here because I want to figure out what goes on top here and what goes on top here. The x squared for sure is going to sit here, right? That's where it sits. So I know that that's an x and that's an x. The number, the single number that doesn't have the x, the constant term, is always going to go in this bottom right corner because that's where you have, oops, I put the x in the wrong place. Nope, you don't go there. You go there. Okay. The number is going to be a constant times a constant. So you're going to get a constant. So the 12 must sit here. All right. So now what can these numbers be to multiply to give 12? Well, okay, probably 3 times 4. All right, that'll give 12. Well, let's check if that's true. So this part's fine. This part's fine. Now let's multiply. The area of this one would be 3 times x, which is 3x. And the area of this one would be 4 times x, which is 4x. Now when I add these up, do I get the question that I started with? And I don't. I get 7x. So that means that this is not right. Those numbers, the 4 and the 3, are not right. So what else could go there? So let's try other things. What else multiplies to give 12? 1 times 12. I can put a 1 here and put a 12 there, fill in these boxes, and notice that that's still not right. So what will work? 2 and 6, or 6 and 2, same thing. So this is going to be 2x, this is going to be 6x, and now the whole box works. So now I could say that x squared plus 8x plus 12 is equal to x plus 2 times x plus 6. All right, and so what did I just do there? I factored. And what was, let's see if you remember, what was this type of expression called? So it's not a binomial because it's got 3 terms. Okay, so it's a trinomial, and it's a special kind of trinomial because there is nothing in front of this x squared, right? Nothing means there's a coefficient there that's a 1, right? And so when the coefficient is 1, it's called a simple trinomial, okay? Trinomials look like ax squared plus bx plus c. Those are the ones that we're going to factor. And in the simple trinomials, this a is equal to 1. All right, next. I'll show you one more, and then that'll be it for this. Okay, so again, I'm going to give you the area. So this is going to be factoring. And the area is going to be x squared minus 25. Okay, that's equivalent to saying factor x squared minus 25. So what's going to happen? So I'm going to, I need an x squared, so it's going to be one of these with the 4 parts. So I can get an x and an x and an x squared. And here's my negative 25. Okay, and so I need 2 numbers that will multiply to give me negative 25. Right, and there's really like no choice here. So 5 and negative 5 is all it's going to be. So 5 times x is 5x. Negative 5 times x is negative 5x. When I add them all up, these two are going to cancel out, and I'm going to be left with x squared minus 25. So I know that x squared minus 25 is equal to x plus 5 times x minus 5. And this is a special kind of expression when this first term is a perfect square. Means it can be written as something squared, so it can be written as x times x or x squared. This one is also a perfect square, so it can be written as 5 times 5, and between them is a minus, or in other words, a difference. That is called a difference of squares. And we learned last year to factor a difference of squares, so I'll go a squared minus b squared is equal to a plus b times a minus b. All right, and that's why it happens, is because this will give you the a squared, this will give you the b squared, and the a plus b gives you, sorry, the ab, okay, I'm going to do it again. If I hold on, let's go back to black. If I drew this as a plus b and a minus b, then this is my a squared and this is my negative b squared, so just like here. And this is an ab and this is negative ab. And these two, the ab and the negative ab, will cancel out, leaving me with only a squared minus b squared. Okay, and so the rectangle model or the area model shows you that the two middle terms will cancel out. Okay, and that's it. So I hope that made some sense. And so we'll be using area models for all kinds of things, factoring. You may remember the term completing the square from last year. We'll be using area models for completing the square. Once again, I'll reiterate, you don't need to always draw the area model. If it helps you, by all means use it when you're expanding and factoring. If it made sense to you, but you're okay without drawing the rectangles, then you don't have to draw the rectangles. It's just another way to help you visualize and make sense of it. Okay, thank you for watching. See you soon.